Hi, I'm a fourth-year undergrad at the University of Toronto, and here's one project I did with Professor Yanqing Wu that I'll talk about. Um, I'm going to talk today about what can the orbits of multi-planet systems tell us about their formation. So the Kepler project has been obviously a great success as it found thousands of planets and planet candidates. One of the interesting things they found was a bunch of these planet systems with many planets that are very tightly packed. And they're so tightly packed that a poster child would be Kepler 11, where you have 6 planets, all super-Earths, within the orbit of Mercury. And these planets are quite interesting from a dynamics perspective because not only are they very tightly packed, they seem to be very dynamically cold. As the previous speaker, Daniel, talked about with his TTV method, you can get the eccentricities of these planets, and it's about 2%, so very low eccentricities. And another thing about these high multiplicity planet systems is that one obvious hypothesis, you see all these low multiplicity planet systems, you might guess, well, are these really just high multiplicity planet systems? But with the geometries of the transits, such that you're missing a lot of the planets, so you're only seeing 1 or 2 when in reality there's 6 or 7 and you're missing them. And so Sarah Ballard and John Johnson have done this study last year where they looked at only M dwarfs, and they have to conclude that no, that's not the case. There actually seems to be a dichotomy in the Kepler planet systems where there's a population of very many planets that are very cold, and then there's a population that's only got a single planet or 2 planets that are very eccentric and highly inclined. So from this picture, basically, we say if we pretend that all these systems are actually high number of planet systems, then we actually have an excess of single planet system that's 4 times as much as you would expect from the single population hypothesis. So this would imply that there's about 25% of planet systems are these genuine large planet systems, and then there's 75% are these dynamically hot ones, which are just a single planet. So to talk a little bit more about these cold planet systems that's the focus for our investigation. They generally have very low eccentricity, so 2%, and also very low inclination, so about the order of 1 or 2 degrees. And they're very tightly packed. So in our study, we used a unit called K, which is simply the distance, the semi-major axis difference of 2 adjacent planets in the units of their mutual Hill radius. And the mutual Hill radius is defined here. It's a very convenient unit that's dimensionless, and it would scale with the semi-major axis. So our question is, these dynamically cold systems, they're so closely packed, are they actually gravitationally stable? And to answer this question, we use brute force. We simulate 20,000 fake planet systems for 30 billion orbits each, and then we did a statistical binning of them to see what's the stability probability given these parameters. So in our simulation, we took all super-Earths, so 3 to 9 Earth mass. We set them on flat coplanar initial orbits, and there's 7 planets, and all the initial Euler angles are randomly distributed. Okay, and so this plot gives you the survival probability as function of this K parameter, the spacing in mutual Hill radius. And you can see that, for example, if I want survival to 10 million years, sorry, this is 100 million, survival for 100 million years is this purple curve, okay? So if I start with only 8 Hill radius, then you see that none of the systems will survive by 100 million years. But as I increase the spacing to about 11 Hill radius, then all of them will survive. And one funny thing is this unit here, K effective, is because your system has 7 planets, and not every single planet will be spaced identically. So an obvious way to think about the dynamical packing is to take the average of this K, because you have 1K for every single pair of systems. So if you have 7 planets, you can have 6K. So an obvious unit would be simply average it, but then actually you have to make a correction, because when you're spaced unevenly, planet pairs that are closer than the average will have a disproportionately more destabilizing effect. So then we take into account this correction, and then we see that if you want a planet system to be stable for a giga-year, if you want half of them to survive by a giga-year, then you need a spacing of 10 mutual kiloradius. So this is our stability criterion. So those set of simulations was done for flat and coplanar. So what happens if you add some eccentricity and inclination? So this plot, this K50 is the same as before. So I'm telling you, if you are above this K50, then you have more than a 50% chance of surviving to, in this case, 1 million years. And you see, as I increase the eccentricity from 0 to 5%, the spacing you need increases from 8 to 14. So even a tiny amount of eccentricity, I'm talking about 1% increase in the average eccentricity of your planet system, will mean that you need to space the planets on average 1 hiloradius more. So it's a very significant effect. On the other hand, inclination have a more mild effect, but also will destabilize your planet systems. So this is our theoretical investigation. Just to recap, you need 10, K equals 10 if you're flat and coplanar, and increases with eccentricity and inclination. So our friend Daniel has told us that most of the planets have an eccentricity about 2%. So that will increase it so that your K critical, the critical spacing is 12 mutual hiloradius for the kind of eccentricities and inclinations we see in the observed Kepler multi-planet systems. So how does that compare to observations? Well, so I took all the planet pairs that have more than 5 planets, and I plot them in a histogram. This is K, and you said there's a dramatic increase in the occurrences beyond K equals 12. And see here, my criterion is 12.1, and here's the histogram. So this is, and also I calculate the average K effective, and I see that it's 12.3. So what it's telling me is that our multi-planet systems with 5 or more planets are extremely close to the edge of instability. If they were any closer, then they would not be stable by a billion years. So that's our conclusion. And what does that tell us about their formation? Well, if they've been carved, if you're so close to the edge of instability, that must mean that there was previously more unstable systems, and as time increased, the unstable ones died or something happened to them. And that's our hypothesis. So your planets form over a time period of about 1 million years. And so when you form these planets after this planet formation stage, the planets are only guaranteed to be stable for 1 million years, the planet orbit arrangements. So whatever happens after that will depend on whether you're spaced far enough or not. So the planets, after formation, you'll see that they are carved gradually by time due to gravitational instability. And the multi-planet systems we see today are the ones that are left that survive this carving by dynamical instability. Whereas the other ones, we hypothesize that they're going to go through a series of collisions, and these collisions will generally produce impact velocities on the order of several escape velocities, and that would basically break up the planet, and you're going to lose all the mass into the sun or eject it out of the system. And whatever's remaining will be very anemic and very stable. And that would be a hypothesis that explains the dichotomy between this hot population and the cold population. So here is summary, and I'm happy to take questions. Eric.
So I know this is a little bit beyond what you simulated, but maybe you could speculate about it. So your implication is that there used to be a lot more multi-planet systems,
yeah.
And the unstable ones have gone away.
Yeah.
Roughly, would this be consistent with every planet forming in a multi-planet environment, and then what we see today is just the leftovers of some instability?
Right. So to be honest, I haven't thought about this because I'm undergrad and my knowledge is
What's your wild speculation?
I think no. I think there's got to be to this picture would require some sort of magical viscous fluid that damps severely the eccentricity inclination in order to form planets that are this close packed. Because people have done these planet formation scenarios like chambers and so on, and they're generally generating planet systems that are way too hot initially to be compatible with this picture. So I'm guessing if you have different disk scenarios, then you could form initially very different kinds of planet architecture.
Dr. Penny?
Do you keep track of the planets that don't survive? How many of them escape, or compared to how many ending collisions?
So this I'm not directly involved with, but it's ongoing research, and basically I think most of the mass will be lost, and it's not clear how many planets are left, but most of the mass will leave, and this is because so they're gonna keep colliding, but most of the time actually the collisions don't destroy the planets. But then even if you're not destroying the planets, you're gonna keep on having collisions because you stir up the system enough that as long as you're unstable, you're gonna keep colliding. So in the end, all the mass will be gone.
But will that go into the star, or will it get ejected out of the system?
That I'm not sure about.
So for your K, you use like a mean value of K minus some steady deviation.
Yeah.
Did you also look at using the minimum K, like your closest two planets?
Oh, right. So the way this unit works is it's like a weighted average, and it's basically taking the average of your smallest half. So I have like 10 planet pairs by K. I take the lowest half is basically what this would do. And we did try minimum, but we see that actually the gravitation instability is a global effect. So even if you have one pair that's quite close together, the average of the whole system still has a destabilizing effect. Yeah.
Did you find that when a collision resulted, if you started out, for example, with 7 planets, then would it be catastrophic and you end up with 1 or no planets, or maybe could you have 5 or 6 planets left over?
Yeah. So to be honest, in this whole ensemble of simulations, we just stopped them when a collision happened because we don't know how to deal with them. That's ongoing research, so I don't know. You can ask Yanqing. Yeah.
Have you tried checking the age of some of these systems with low K to see if they actually are young?
Oh, so we haven't tried, but we did look at the ages, and the vast majority is older than 1 billion year, like 5 or 10. Sorry, 5, not 10. I'm not sure, but definitely most of them, the vast majority is more than 1 gigabit.
Okay, I'm actually gonna, you can ask me during the coffee break, unfortunately. We'll go on. Let's thank Michael.